All right. Hello. 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 Happy Sunday. Welcome. If you're just coming in, welcome. My name is Sam. I am the Physics C Mechanics CRAM teacher. Today we're talking about Unit 3, which is work, energy, and power. So we'll give everyone a moment to jump on. As we're waiting, a couple of things. If you don't have scratch paper and maybe even a calculator around near you, take a moment and go grab that. We're going to do some problems today. And as much as you would like to jump in and do problems with me, I would love it. So grab some scratch paper, say hi in the chat, let me know you're here. And also in the chat, if you could, please put in, we've got a lot of content today and I've got a lot of problems ready, but I would love to know if you would like to focus more on multiple choice or free response questions today. So if you don't mind sticking that in the chat, that would be great. And we will get going in just a second. If you're just coming in, hello, my name is Sam. We're doing Mechanics Unit 3, Work, Energy, and Power. So people are just getting settled. We'll give everyone just another couple moments and then we're gonna get going. And if you wouldn't mind getting some scratch paper so that way you're ready to go for problems. And then if you've got a preference in terms of working on multiple choice or free response, definitely stick that in the chat. I've got a lot of problems ready for you today and would love to know if there's somewhere we want to prioritize. Great, and let's get going because we're already 2 minutes in. So I'm gonna share my screen and we will jump right in. Let me get this going. All right, so like I said, work, energy, and power today. So that's exciting. Let's see if we can do that. There we go. Oh. There we go. Great. So work, energy, and power today. We are going to tackle a bunch of content, a lot of equations, things like that to look at today. Heads up that we are recording this, and so we may use it on things like website, YouTube, other public spaces. And if you've got a question, I might call you out by name, so just be ready. Change your name if you want to avoid that. Always a plug to follow us on different social media platforms. We've got a lot of great resources for you, and this is a great way to find out about them. So Twitter, Instagram, YouTube, any of those. Cool. So in the stream, we are going to talk about the work energy theorem. We will talk briefly about power, and then we'll talk a lot about conservative forces, potential energy, and energy conservation. So a lot of content to crank through today. And so we should really just dive straight in. First kind of subsection here, we are going to talk about the work energy theorem. So we need to talk about what work is first. Then we will talk about the actual theorem, what goes on, how we relate work to energy, and then, like I said, briefly talk about the idea of power. So first is work. So work is, it's an energy transfer, right? And it's caused by a force being applied over a displacement. So if we look, there's two formulas here. The second one, this bottom one, is on your equation sheet, but really the first one is actually going to probably be the more helpful formula because it takes this idea of a dot product, which you can see right here, and it kind of just like simplifies it so that way you can just plug in some numbers and do some math. So if the force is constant, then we know that the work is going to be equal to the force times the distance over which that force is applied times the cosine of the angle between those two vectors. That's kind of how you do that dot product. And so if we just remember to take that cosine of that angle between, that will allow us to find the work, assuming that it's constant. So you can see this In this diagram on the right here, you've got the force. If it's applied at an angle, the y component of the force doesn't contribute to the work. It's only the x component. So we take that f cosine theta to find the x component and multiply it by the distance over which that force is applied. If the force is changing, however, we do need to do some calculus. So we can see here the work is equal to the, well, you have to integrate the force function with respect to the distance traveled. And regardless, work is going to be measured in joules. So a couple more things about this idea that work is a scalar here. So if we look at it, what that means is that work can actually have a positive sign or a negative sign when we calculate it. And it's just going to depend on the relationship between the force that's being applied and the distance or the displacement over which it is applied. So if we look at this chart, the force and the displacement have to go in the same direction. If they're perpendicular, then there is no work applied. If we think about it in terms of the cosine, the math part, the cosine of 90 degrees is 0, right? So there's no work if the force is perpendicular to the displacement. If the force is in the same direction as the motion, so we can see in the second diagram here, the force and the displacement, both vectors point in the same direction, the work done is going to be a positive number. If they're in opposite directions, the work done is going to be negative. We can see at this bottom picture, the force is to the left and the displacement's to the right, right? And then if it's not moving, the work is also going to be 0. So if there's no displacement happening, then there's no work. The work is 0. Okay, cool. So how does this relate to energy? So we're going to talk a lot about energy today. And we can relate the work done on a system to the energy of that system. So work is going to result in changes of energy. That's how we defined it. Positive work means that energy is going into the system, and negative work means we're taking energy out of the system. The work energy theorem is the thing that relates all of those together. So this is the equation. You actually can see this is the same equation that I showed you before. I just added the energy. This full equation is what's on your equation sheet. And what it tells us is that the change in energy of a system is going to be equal to the work done on that system. And then we know that it's also, that relationship is also that the work is related to the force and the distance, the displacement over which the object travels. Energy is also measured in joules. Pretty much everything today, except for watts, except for power, is going to be measured in joules. Sidebar here, we've got a lot of formulas today. So sidebar just here on kinetic energy. Kinetic energy is the energy of motion. Basically, if something's moving, it's got kinetic energy. This is another formula on your formula sheet. And it's the formula for kinetic energy, and it's equal to, K is kinetic energy, it's equal to 1/2 times the mass of the object, which is going to be in kilograms, and then the speed of the object squared, which isn't going to be in meters per second usually. Actually, for it to be a joule, it has to be, right? So this is another one that's on your equation sheet. Today's going to be a bunch of formulas, and really, we could go through how we get this formula for kinetic energy. It has to do with the work function, work in the force function and stuff. But really, if we're thinking takeaways for the test, we just need to kind of know how to use all of these formulas, right? So we've got this kinetic energy formula, and pretty much anytime something's moving, it's got kinetic energy, and it's going to be equal to the mass times the velocity squared. Great, speed squared. Okay. So here is our first sample problem. We've got a person who's going to throw a ball with mass 0.2 kilograms. The ball starts from rest. It's going to accelerate horizontally through a distance of 0.9 meters and leaves the person's hand at 30 meters per second. So we're looking for the force applied to the ball by the person's hand. And you've got some options here. So I will give you a moment to work on it. I'm going to open up a poll question. If you want to share your share what you think you've gotten, here we go. Kristen's also in the chat if you have questions. I forgot to call her out earlier. Kristen is here with us today. She is our lovely TA who can help too. But I'll give you a moment to see if we can't get an answer to that first question, and then we will get going. I'll give you about 30 seconds. All right, we've got a couple votes in. Great. So let me show what you got, and then I will walk through it. So correct response was D, and we got it right. Love it. Okay, so if we were to work through it, I'll go quick because it feels like we've got it. First step, always just what we know, right? Write down what you know. So we know our initial velocity is 0. The velocity as the ball leaves the person's hand is 30. Mass is 0.2, goes over displacement of 0.9, and we're looking for the force. So note here, you could use kinematics and Newton's second law to figure it out, but a lot of times we're going to find that energy equations are actually going to let you do this faster. So this is a work energy theorem question. All of the change in energy is kinetic because it's accelerating horizontally. Hopefully you also noticed that because we haven't talked about potential energy yet here, but all of the energy change is kinetic. And so we know that that change in kinetic energy is going to be equal to the work done. And then we can relate that. If you look at this highlighted part here, we can relate that to that FD cosine theta, right? Cosine, the angle is 0, right? Because it's horizontal. So we just keep that as 0, and we get our force to be 100 newtons, or D. Great. Remember, also, I'll just keep saying it. If you have questions, definitely throw them in the chat. I'll be checking it, and Kristen is here for you too. Okay. So let's talk about power. So power is defined as the rate at which energy is transferred. So we measured in joules per second. So if we think about it, energy is joules, and we're looking for a rate, right? So it's basically how fast that energy is transferred, which is why it's joules per second. We give joules per second a different name. Instead of having to say joules per second every time, we say watts. Like if you think about light bulbs, same idea, watts, capital W. And there's 2 power formulas that we can use. Again, we're not going to go over how all of these are derived, but if we kind of get like the takeaway here, power is either the derivative of the energy function with respect to time, or it's the force applied times the velocity vector. Okay, so here's another question. We've got an electrical motor providing 0.5 watts of mechanical power. We're looking for how much time it will take the motor to lift a 0.1 kilogram mass at a constant speed from the floor to a shelf 2 meters above the floor. So let's try this one. All right, and the poll is open. So if you are wanting to work on the problem yourself and see what you can get for an answer, take a moment and go ahead and tell me what you get. Great, we've got some votes coming in. Take another 30 seconds or so if you're still working, no worries. All right, let's see what we got. So let me do this and show you real fast. So the correct response here was D. Let's go over it because we're about split as between C and D. So let's take a second and look at this one. There we go. So the first thing here is when we look at this, we know that with power, we're looking for either a force and a velocity vector, or we need to figure out the change in energy with respect to time. In this case, they're giving us things like masses and heights and displacements and things like that. So this first thing is like, okay, which one of those formulas are we going to do? And we're going to pick the change in energy with respect to time formula because of the types of numbers they're giving us. So they're giving us mass, they're giving us heights, things like that. So when we look at this, we know that the change in energy is going to only be increasing potential energy. So I'm hopeful this is review. If we've never seen this potential energy function before, never fear, we're talking about it really soon. But this is this change in U equals mg change in Y is something that's on your equation sheet. And all we need to do is figure out what that change is as we lift the mass from the floor to a shelf. Note that it says a constant speed. That's very much on purpose, because what that's telling us is that there's no change in kinetic energy because the speed is the same. So all the changes is potential energy, and we can figure out how much that is. And then from there, we know what the power, we know what the watts were, right? So we can plug in and solve for our time. So reminder, if you have more questions, stick them in the chat. And we're happy to talk about that one more if needed. Okay. So we're going to keep cruising. We're going to cruise on to our second section, which is conservative forces and potential energy. So we're going to talk about what it means to be a conservative force first, and then we are going to dive into potential energy. So first thing here, conservative versus non-conservative forces. So hopefully you were with us for our last CRAM. We talked a lot about forces. Forces will come up again kind of at different points throughout this this series, but here's one place that forces especially come up related to energy. And we have to add some new definitions to our force ideas. So there is a difference between something called a conservative force and a non-conservative force. And it has to do with whether or not, as the object moves through a closed path, and I'll show you what that means in a minute with a picture, and as it like kind of goes through a path and returns to its initial position, if the work done on that object is 0, we define the force as conservative. Another way to say that is that no matter kind of like where the object goes, the path of the object doesn't matter for conservative forces. So really the two big examples of this that we'll hit in this unit are gravity, so gravitational force, and elastic force. So that's like springs or like rubber bands or other elastic-y type things. The opposite of that is a non-conservative force. So if you're moving through that closed path and return to initial position, if the work done is not 0, then the force is, that's a typo, the force is not conservative. And what that means is the object's path matters. So examples here include frictional force, right? So think about it, if you go on a longer, if the path is longer, more friction will happen because you're going for a longer distance. And drag force, which is really just another type of frictional force, right? So friction's kind of the big non-conservative force to keep an eye out for. Here's a photo. Again, our lovely TA, Kristen, sent me this photo, and it's a great one. So if we take a look at these paths, all 3 of them start at point A and end at point B. They're just different in terms of the path that is taken between A and B. If, when you look at all three different paths, the work done for all of them is the same, then by definition, you've got a conservative force. So if we think about it, if you're lifting something up, maybe in that previous problem, from the ground to a shelf, it doesn't matter if you lift it straight up in the air or you lift it and kind of like move it in like a weird, awkward, zigzaggy path and get it to the shelf. As long as you start and end in the same places, then the work done on that object is going to be the same, versus a non-conservative force, which is the path does matter, right? So the work done, if we think about like friction, the work done by friction in the red path, path 1, is going to be different than in the green path or the blue path. So that's conservative and non-conservative forces. And the reason it matters is because when we're going to start talking about potential energy and energy conservation, whether or not the forces acting on the system are conservative or non-conservative is going to change how we approach the problem. So here we go, potential energy. So potential energy is the energy an object has due to its position. There's different types of it. But regardless, there's a really, really, really important relationship. If there's one thing you're taking away from this stream today, it is the relationship I'm about to talk about. You can see I boxed it in multiple colors because it's that important. It's also important to remember because it's not on your equation sheet, but it comes up all the time. So we have to just like know that this is a relationship that exists between force and potential energy. And it's this, right? So the force function, as long as it's a conservative force, so as long as it's either like gravity or the force of like a spring, something like that, as long as it's a conservative force, then it's going to be equal to the negative derivative of the potential energy function with respect to x. So this relationship is something that's again, you can derive it. We're not going to do that today, but it's super important. And so remembering that we can relate the conservative forces to potential energy through this relationship is going to be really just like a really important thing to remember for the test. Also, don't forget that it's the f of x is equal to the negative derivative of the potential energy function. So I'm going to stop harping on that, but really, really important, which is why I'm talking about it for so long. Little sidebar. Again, we're just throwing so many equations at you today. We also have a different equation for gravitational potential energy, right? And so specifically, potential energy due to gravity, it's the energy that an object has due to its position relative to the Earth. And the equation for it is going to be the change in gravitational potential energy is equal to the mass times g, which is 9.8, right, times the change in height in meters of an object. Okay, more practice. Here we go. So this is taken from the 2012 practice exam. All of these questions also, by the way, that I'm getting to you are all public, right? So if you Google these, physics C, mechanics, old practice exams, these will come up. So definitely, as we're getting closer to the test, starting to kind of look through these and do some practice tests in their entirety will be super helpful to you. So here we go. Number 20, certain one-dimensional conservative force is given a function of x by the expression F equals negative kx cubed. F is in newtons, x is in meters. Possible potential energy function U for this force is. So I'll open up the poll again, see what you can do with this one. And then see how you're doing. So take a second and see what you can come up with. Take another 15 seconds or so. All right. So this one we didn't get, which is okay. So let's talk about it. So correct answer here is C. If we take a look, we can do two things. We know that the force is going to be equal to the negative potential energy, the negative derivative of the potential energy with respect to x. So we can either do it one of two ways. We've got the force function, so we can either integrate with respect to x to get our potential energy function, or another way, because this is a multiple choice question, what we could do is we could just take the derivative of each of the A, B, C, and D and see which one matches the force function. So I think probably for those that, especially those that picked B, there was a good amount that picked B. I think we just went in the wrong direction. So instead of taking the sort of integrating here, we took a derivative. So if we integrate, we see we need to take the negative, integrate and then take the negative, right? So if we do that, we see that we get 1/4 kx to the fourth. And then we don't know, it's plus c, but because we don't really know, it says a possible potential energy function will give us, the only one that's possible is this one, right? Because that's the only one with the proper x to the fourth. So we just went in the wrong direction. Again, if you have questions about that, definitely stick them in the chat. We're going to do a couple more of these just because they really, I feel like I see them on every multiple choice practice test that I see. So here's another one. This time we're given a potential energy function with a couple of constants, which is an expression for the force on the particle. So I will open up another poll here. See what we can do with that one. All right, take another 10 seconds. Nice, great. So let me show you this one. Correct response was A, and we got it right. Love it. Okay, so just briefly, we got that one. So I won't spend too much time on it, but we're given a potential energy function with some constants in it. And always, once we're given, we need to find the relationship. This, again, is the same deal, same practice. Force function is equal to the negative derivative of the potential energy function. So we need to take a derivative of the potential energy function to find the force. So if we take the only weird thing, math thing, is if we take the derivative of c in the function, we know c is a constant, and so that goes away, right? Because the derivative of just a number is 0. And then we make sure that it's that negative derivative. So we get our final answer of A. Love it. Okay. One more. This one's a little different because we have to definitely relate force to potential energy again, but then it specifically asks us what is the change in potential energy when the spring is stretched 2 meters. So this is not a find a function question. This is an actual calculate a number questions, which is why we have it in here. So take another couple moments and see if we can't get that one. Let me open the poll. When you're ready, go ahead and choose. Take another, 15 seconds. All right. So we're split on this one. So let me show you. Correct response here was 64 joules. Some of us had 56, some of us had 64. So let's take a look at what this looks like. So first, always, what are we given, right? So we've got our force function here, and we need to know about potential energy. So we are, again, going to relate the force to the negative derivative of the potential energy. And this one is just like, not the last problem, but the problem before, where we need to integrate. This time, though, we are going to integrate that force function, and we're going to do it with some actual numbers, because we know that we're looking for that the spring is stretched 2 meters from its equilibrium position. So let's dive into it a little bit. So if we look here, we're going to stick in that force function here, right? We want to know the change in potential energy. So that's going to be from the initial to the final. That's how we're going to integrate, and we're going to stick that force function in on this side. We're actually going to do the integration. So if we do that on the left side here, we get the change in potential energy. If we do it on the right side, 40x minus 6x squared becomes 20x squared minus 2x cubed. Remember, the exponents are getting bigger when we integrate, right? And don't forget that negative sign, because that's it's the negative derivative with respect to x. So once we do that, we're gonna integrate from 0 to 2 meters. So the way we do that is we plug in 2 for x, and then we're gonna subtract 0, right? But when we plug in 0 to this integrated function, it's all just 0, right? So all it is 20 times 2 squared minus 2 times 2 cubed. We do some math, and we actually get negative 64 joules, but I put a little note in here for you all. Your answer is negative because what you were solving for, the f of x given in the problem, tells us about the force applied to the spring. It asks us about the force of the spring. And so this is just a Newton's, it's kind of annoying actually, but it's like a little Newton's third law tie-in, where if we know the force applied to the spring is negative 64 joules, then Newton's third law tells us that the force of the spring is equal and opposite. So it's going to be positive 64 joules. So that's that one. Again, if we have questions or want to chat more about it, definitely that's what the chat is for, right? Okay, cool. So then now let's dive into conservation of energy. So 2 things here, and we're going to do some free response practice with these too. So first one, using the law of conservation of energy, talking about what it is, how we use it, and then we're going to talk about a special case in springs. So this equation gets its own slide. That's how important it is. The total energy in a system is going to, by definition, equal the change in kinetic energy plus the change in potential energy plus any non-conservative work done by non-conservative forces on the system. So this is going to be a kind of a guiding expression that you're going to use for anything that's talking about energy moving forward. If there's kind of like a special case of that. So if there's only conservative forces acting on the system, then the total energy of the system always stays the same. So if there's only conservative forces acting, then we know that the law of conservation of energy will hold. And what that means is that we can go from more kinetic to more potential energy, or more potential to more kinetic, but the total energy in the system is always going to be the same, which means that the total change in that energy is always going to be equal to 0. So you've got this GIF here. That's Neil deGrasse Tyson. And he is looking at this. This is a pretty classic physics experiment that you may have seen, where as long as you start maybe like a bowling ball, as long as you start the bowling ball with no speed, I broke it, with no speed, it's going to come back up to the same height and go no higher, therefore not smashing his face in. So definitely, if you want kind of the extended explanation of that, this is all over YouTube. Definitely you could look up, this experiment. It's a pretty classic physics one. But this, if you're thinking conservation of energy, this is a nice one to just kind of like, if you need a visual, think about the bowling ball on the pendulum. Okay, so good. We've got lots of time. I wanted to really dive into a couple of free response questions, because we now, if you've been following along in the CRAMs, we now, I feel like, have enough info to really start to kind of dive into the free response, which usually pulls from more than one unit. So for this first one, this comes from the 2009 test. I will also say that this is also something super Googleable. All of the old free response questions are not protected behind any sort of like login. If you just go to the College Board website, they're all here for you along with the answers, so that way you can check them out. But I pulled this one from the 2009 exam. And we're going to do A and B, and then we're going to actually not do C. We're just going to do D, because all of those are relevant to what we're talking about. So we're going to go through this letter by letter. I've got more polls for you, so that way we can test how we're doing. So we'll do A first. So we've got a 3 kilogram object moving along the x-axis in a region. Potential energy as a function of x is given by U of x is 4x squared. Using joules, x is in meters. When the object passes point x equals negative 0.5 meters, the velocity is 2 meters per second. And then it says all forces acting on the object are conservative. I am going to let you work on this. I will say that that sentence, all forces acting on the object are conservative, is going to be really important, because we know that if the forces are conservative, we can use conservation of energy. So that's a little bit of a spoiler. But with that, I will give you a moment to see if you can get an answer for A, and I will open up a poll. Thanks, Kristen. Yeah, I just saw your note about loving this experiment. I love it too. I'll open up a poll to see if we can get the total mechanical energy of the object. So take a moment, see what you can do. And we'll walk through it too, of course. So if you need a place to start right now, what I would tell you is that we've got a position given that tells us about the velocity or the speed of the object. And based on that position, we could also find the potential energy of the object. So I would point you towards using that negative zero .5 meters as a place to see if you can't find that total mechanical energy. And I'll give you another, I don't know, 30 seconds. Okay. Okay, great. So let me show you. We're split on this one, which is great. That means we should talk about it. So half of us got 7 joules, which was the correct answer. Half of us got 10. So let's walk through what this looks like. So first thing, especially with free response. I know free response can feel at least for me, every time even to this day, every time I look at a new free response, I feel a little intimidated or a little just like, okay, there's a lot of things here, a lot of questions to answer. Got to just like take a deep breath and unpack, right? So the first thing here is just to kind of like unpack the problem. What info does it give us? So in this problem, it gives us a potential energy function. So it says U of x is equal to 4x squared. Tells us the mass of the object, it's 3 kilograms. Tells us that at x equals negative 0.5 meters, our speed is 2 meters per second. And it says that there's only conservative forces. So that's a lot. That's actually like, it might not feel like a lot because that list is not very long, but that's actually a lot of info to be able to work with. So biggest thing is, and I said this as we were first reading it, because it's only conservative forces, I can use conservation of energy to help me solve this problem. That's huge because that means that I don't have to worry about the work done in this problem at all. All I'm looking at is what's happening with the kinetic energy, what's happening with the potential energies. So next, we're going to answer the question. So for A here, we know that, like I said here, the work is 0, so we don't have to worry about it. So all I need to do to find my total mechanical energy is figure out what my potential energy is at that x equals negative 0.5 meters, and then what my kinetic energy is, and I'm going to add them up. So I used my potential energy function and plugged in negative 0.5 and got that my potential energy is going to be 1 joule at that point. And then I used my kinetic energy formula so that, because I know the mass and I know the speed of the object at that point, to get 6. So then my total energy is going to be 7. Again, this is, I know there's like a lot of formulas here, but really just thinking about what you're looking for and which formulas will help you get there is helpful. So that's A. So let's look at B. B says calculate the x coordinate of any points at which the object has 0 kinetic energy. So now we know the total energy, and the problem definitely asks us to find that first for a reason. So we know our total energy, and we know that the object has to have 0 kinetic energy. And we know energy is conserved. So those were 3 big hints to get you started. So energy is conserved. Total mechanical energy we just calculated as 7. And then we know that we want 0 kinetic energy. So let me open up a poll and see what we can do here. So as you're working, if you need a place to start, we know that the total energy of the system is 7 joules, right? And if we know that if there's no kinetic energy, that all of that energy must be potential energy. And we've got a function for the potential energy. Take another 15 seconds or so. All right. Okay. So we are going to pause here. I think some folks are not answering because I think they're stuck, maybe. So, which is fine. Or we just don't have time. So let's look at B. This is B right here. So remember that energy is conserved, right? So all points will have 7 joules total of energy. And we know that if there's 0 kinetic energy, that all of the energy has to be potential energy. From there, don't overthink it. We know that the energy is potential energy. So all we're going to do is we're going to take that energy number and we're going to plug it in for U. So we know that the total potential energy is 7, or total energy is 7. So, and it's all potential energy. So 7 equals 4.0 times x squared. And then we're just going to solve for x. Reminder that when we take a square root of a number, we can get the plus or the minus of that number, right? So when you take the square root, if you put it into your calculator, it will give you 1.3 probably, but remember that that could be plus or minus, positive or negative 1.3. Again, if you have questions, definitely stick them in the chat. Happy to talk. But that's it for B. So last one here, like I said, we're skipping C. So for D, calculate the magnitude of the acceleration of the object as it passes x equals 0.6 meters. So this is definitely, this is the one that you have to pull in lots of info from lots of places. Hints, I guess, as you get started here. Remember, acceleration we can relate in a couple of ways. We can use acceleration as it relates to force using Newton's second law. Acceleration also shows up in our kinematics equations. So there's actually a couple ways to solve this D question. And yeah, I don't want to tell you too much. So I guess see if we can't find a path to get from potential energy and kinetic energy to acceleration. And there's going to be a couple of steps that we have to take in order to get there. So take a couple moments for that one. Polls open when you're ready for it. And I'll definitely talk through it too. Take another 20 seconds or so. All right, great. Okay, so let's look at D here. So again, the first thing we want to do is just figure out, what are the relationships do I need to kind of draw myself a path to get from the info that I know to the info that I'm looking for. So in this case, like I said, you could use kinematics and go that route. because we talk so much about that force equals the negative derivative of the potential energy function, that's the one that I liked. So that's the one I went with. So we know that the force is equal to that derivative and that the force is equal to the mass times the acceleration. We're looking for A, right? So first, in order to get A, we have to know what the net force is. And it's this potential energy relationship that's going to get us there. So if I take the derivative of the potential energy function with respect to x, that will give me a function for the force. So if I do that, I get the negative derivative, right? So if I do that, I get negative 8x for a function for my force. From there, I can use Newton's second law, F equals ma, right, to get to the acceleration. So if I plug in my force function into Newton's second law, I get 8x equals 3 times a. The 3 comes from the problem tells us that the mass is 3. And then if I solve, I get an expression for acceleration to be 8x over 3. The problem explicitly asks us about or about what's happening at 0.6 meters. So what I did is I just plugged in 0.6 for x, and I got a to be 1.6 meters per second squared. Cool. I also wanted to show you here, you can access these slides, I think, in the resources section, but I also put in the scoring guidelines for this problem, just so that way you could kind of see how it works, right? So when the readers are looking through your work, they've got these. This is kind of like a guideline to give you as many points as possible. So just even recognizing that to find the total mechanical energy will be potential plus kinetic gets you a point, right? For recognizing that in B, that all of the energy is potential at that, when the kinetic energy is 0, that gets you a point. In D, there's a couple different ways you can do it here, right? For just writing down this expression, this F equals negative du dx, that gets you a point, right? So definitely writing down as much as you know will help you as you're working on free response. Cool. Last thing here is springs. So springs are kind of a special case that comes up a lot, especially in this energy section. And there's 2 equations on your equation sheet that are specifically for springs. So the first one, it talks about the force of springs. And it's right here. So the force of a spring is going to be equal to negative K. K is a constant. It's called the spring constant. You have to either be given it or you could solve for it, but it's not super intuitive. And it has to do with how stretchy a spring is, right? So it's basically how much force it takes to stretch a spring a certain distance. So its unit is newtons per meter, and the x is the distance that spring is stretched or compressed. And this is the formula, right? So the force is equal to the negative spring constant times that change in x. These only work for we call them linear or ideal springs. If it's not a linear spring, they'll give you a force function or ask you for it, right? Potential energy, spring potential energy. It's also a special case. It's the stored energy due to a spring. So if you think about if you were to push or maybe pull apart like a slinky or a spring or even like a hair tie or something, when you let it go, it would go back to its equilibrium state. That's potential energy, and it's going to be equal to 1/2 the spring constant times x squared. So we only have a couple moments left, but I do want to at least take a look at this. So maybe we won't do this as a full pull question problem, but I'll at least give you a moment, or I'll at least talk through it so that way you can see it. Here we go. Black starts at rest on top of an inclined plane with a height h, goes down the plane, and keeps going, collides with an ideal spring constant K, negligible friction. So there's no, everything's conservative, right? Because there's no friction. And it tells you to express all the answers in terms of m, h, k, and physical constants as appropriate. So first question here is derive an expression for the speed of the block just before it collides with the spring. So if we look at that, here's what we would do. First, we're going to unpack the problem, right? So we know from the problem, M, H, K, those are all okay to have in our answer. We also know there's no friction, as I said, so it's only conservative forces, and conservation of energy is okay to use. I also drew a little diagram here to help me unpack. So I know that if it starts from rest at the top of this ramp, all of my energy at this point is going to be gravitational potential. At the bottom of the ramp, all of it's going to be kinetic. And then once the spring is compressed as far as it will go and the block stops, then all of my energy will be elastic potential energy. Great. I know that I've got this relationship because energy is conserved. And I know that I've got my little equations for each of the different types of energy. So I know my kinetic energy is 1/2 mv squared. My spring potential is 1/2 kx squared, and my gravitational potential is mg change in h. Okay, so A wants an expression for the speed of the block just before it collides with the spring. So the way I'm going to do that is I'm going to say, okay, I know that if I add up all my energies as this goes along, the change is going to be 0. I also know that at the top, it's all gravitational potential. At the bottom, it's all kinetic, and there's no spring happening yet. So this spring equation can just go away for this problem. So what I did here is I just set the total kinetic plus the total gravitational potential equal to 0. And then I just solved for an expression for the speed of the block. And I can leave in h, right, because it told me I could, and I can leave in g because g counts as one of those physical constants that they're talking about. Great. The second question says, is the speed halfway down the incline greater than, less than, or equal to 1/2 the speed at the bottom of the incline plane? So that's just like a whole mouthful, right? But easiest way for me to figure that out is to just plug in, see what I can figure out, and then plug in numbers. So what it's asking is the speed at the bottom, we've got an expression for. It's asking about the speed halfway up the ramp. So if we're halfway up the ramp, then my height is going to be 1/2 of the total height of the ramp. And then I got an expression for the speed halfway up the ramp. From there, when it's like greater than, less than, whatever, that for me is like, my brain doesn't work in ratios very well. And so what I do is I plug in numbers. So I know that I'm just going to be like, okay, maybe the height's 10. Maybe the ramp's height is 10. If that's the case, I can find the speed at the bottom of the ramp by plugging in 10 here. And then I've got an expression for halfway. So I plugged in 10 here. 9.89 is more than half of 14. So my answer is going to be greater than. That's how I figure it out. You can just look at it, but for me, that doesn't work. So I plug in numbers to see what I can get for answers. Okay, I know we're running short on time. Last one, derive an expression for the max compression of the spring. So if we're going to do that, we're going to revisit this conservation of energy equation. This time, though, I'm going to look at the top point where all of my energy is gravitational potential, and then I'm going to look at the max compression point when I know that all of my energy is elastic potential. And I'm going to do the same thing I did in the first part, right? Except for now, I'm going to solve for x. So all I did is I got rid of that kinetic energy and then plugged in what I knew for the different heights, solved for x. Okay, great. I put in the scoring guidelines for you again, so that way when you're looking at these slides again, if you would like to kind of unpack the scoring guidelines, they're here for you. And then lastly, just to wrap up, I know that there was like a crap ton of formulas that I just threw at you that are on your equation sheet, but that is both can be like, oh man, which one? But it also can be super helpful and powerful because you're like, if I don't know what to do, I'm just going to start pulling out formulas that I know have to do with energy and see what I can get from them, right? And kind of just plug in stuff and see where I can go. So use your formulas. They're here. They're on your equation sheet for you to use, right? So use them. If you don't know where to start, just start plugging stuff in and see where you can get. As always, list what you know, what you're looking for, draw a diagram. A lot of times energy equations are faster than trying to use Newton's second law or kinematics. So if you keep practicing and become comfortable with them, they actually will also help you save time on the test. And I think that is it. So I will stop talking. Last couple plugs, upcoming events. Unit 3 trivia is tomorrow at 9 Eastern time. And then our next CRAM will be next Sunday at 2 p.m. this time. And we're talking system of particles, linear momentum. Kristen will be popping over to Discord. Keep this convo going. Definitely head there. And she is happy to help chat too with questions or just want to debrief a little bit. Again, I knew I threw a lot at you. So I think this would be Kristen's a great resource for you too. I'll stick around for a minute in case anyone wants to throw anything in the chat, and then we'll be done. So let me stop sharing. Great. Ooh, the light. Cool. I'll stick around for a moment, throw anything in the chat. Otherwise, thank you so much for your work today. It's good to be with you all.